Okay, so in this video, we are going to learn about the built-in functions related to normal distribution in R. Again, just like in all previous examples, we are going to use the prefix d to represent the probability density function for normal distribution, and d norm will help us to calculate the probability density function of the normal random variable, which is here, which is a complicated function with an exponential function which has a quadratic function in the power. So we can calculate, for example, the probability density function of 2 with location parameter or mean equal to 0 and the standard deviation or the scale parameter being equal to 1. So this is called what? So if the location parameter is 0 and the standard deviation or the scale parameter is equal to 1, this means this is a standard normal random variable, and this calculates the probability density function for a standard normal random variable. Okay, standard normal random variable at 2. But remember again, probability density function values do not mean anything. Okay, they do not represent anything, the probability density functions. They are not calculating probabilities. They are just indicating the relative likeliness for that value compared to any other possible value. Okay. So if you do not write the location parameter as 0 or the scale parameter as 1 as the second and the third argument here, again, by default, the d-norm function will assume a standard normal random variable. In fact, you can check the d-norm function and the details about it. Now, if you are just going to get a web page, you see the second argument is the mean or the location parameter, and the third argument is the standard deviation or the scale parameter, and by default, they are always equal to 0 and 1 respectively. All right, so you can also calculate the probability density function in another parameter setting. Let's just say the location parameter or the mean is 5 and the scale parameter or the standard deviation is 3.5. And we are interested in the normal density. Again, this is a mistake. I need to change this to normal, not exponential. I need to write here. So normal density at 2 is calculated with this function. So d norm 2 at 5, location parameter 5 and scale parameter 3.5. Of course, you are going to get different value in this case. Now, how can we calculate the probabilities then? Remember, for continuous random variables, the function that helps us to calculate the interval probabilities or less than or equal to probabilities or greater than probabilities is the cumulative distribution function, which calculates us the probability of that certain random variable to be less than or equal to x. Now, let's just say I am interested in calculating the probability of my standard normal random variable z, okay, to be less than or equal to 2. Now, remember, so far, we have learned that it is easy to calculate this probability using the table, CDF table, right? So if we want to calculate the probability of a standard normal random variable to be less than or equal to 2, we need to check 2 from this list, and it is 0.9772, right? Now, of course, you can also calculate that probability with PEXP function, where P stands for cumulative probability. I'm sorry, not EXP, sorry, norm this time, right? P norm function. You can use the P norm function of 2, again with the standard parameters, 0 for location and 1 for the scale. And you also get the same value here, 0.9772. Or if you do not write these parameters, still you get the same thing, because by the default assumption, we assume a standard normal distribution if no parameters introduced. All right, so another question here. What is the probability of any non-standard normal random variable? Let's just say this time we are talking about the normal random variable with location parameter 3 and scale parameter 1. And what is the probability of it to be less than or equal to 6? So this time, what you need to do is cumulative probability at 6 with location parameter equal to 3 and scale parameter equal to 1, and you are going to get these answers, 0.9986. So all probabilities related to normal random variables can be calculated using this p-norm function. In fact, in the next question, we will practice it. However, again, we need to learn the inverse CDF for the normal distribution. So let's just say we are interested in the inverse CDF, which means instead of asking a probability of this random variable to be less than or equal to a certain value, this time we are going to give the probability and we will say that for which value the probability of this random variable to be less than or equal to is equal to P. So this time we will ask P and we will give P and ask X, which means the inverse CDF at the probability. So let's just say for a non-standard normal random variable with location parameter 1 and scale parameter 5 and scale parameter 1. For which value the probability of this random variable is less than or equal to 0. For which value the random variable is less than or equal to with probability 0.5 is being asked. Now we are going to answer this easily. Of course, 5. Remember, the location parameter separates the distribution into two equal parts, right? Because of the symmetricity of the normal random variable. Therefore, the answer should be 5. Okay, so half of the possible values is less than 5, and the other half of the possible values is greater than 5 because the location parameter is the center of this distribution. Therefore, the answer is easy. However, if you still want to prove that with this calculator that you have here, you can use Q norm. The distribution probability, the separator probability is 0.5, and the location parameter is 5, and the scale parameter is 1. You will get this thing. Now, let's just say I have a normal random variable with location parameter 5 and scale parameter 2, and I'm interested in the certain value x for which the less than or equal to probability for this random variable is 0.95, or in other words, 95% of the possible values that it can take should be less than or equal to x. So we are interested in that threshold, which is the inverse CDF at 0.95. So we are basically asking this cumulative probability to be equal to 0.95, which means we are asking the inverse CDF at 0.95 with this parameter setting. Therefore, we need to write Q norm 0.95, and the location parameter will be 5, and the scale parameter will be 2, and that value is 8.29 approximately. Now, let's check. What is the probability of a normal random variable with location parameter 5 and scale parameter 2 to be less than or equal to 8.2897? That is, as you can see, approximately 0.95. Because I have not exactly introduced that value, I couldn't get 0.95. But if you want to continue like this, of course, you are going to get the exact value 0.95. Okay, so this is how the inverse CDF function works. So the trick is easy. D density, P cumulative probability, Q inverse CDF. Okay. Okay, so let's solve a practical question now. It says the service time of a teller to clients in a bank. Okay, so in a bank, the tellers are working, so the clients are arriving and they are either depositing money or withdrawing money or doing something else. For example, they can borrow a loan. So they will talk with the tellers, and the service time of a teller is normally distributed with a mean of 8 minutes and a standard deviation of 30 seconds. So what does that mean? So if you go to a bank and when it comes to you to serve, the time the service will take is normally distributed. On the average, a service is complete in 8 minutes. However, because it is random and normally distributed, there's also a standard deviation or scale parameter, which is 30 seconds. However, remember, you need to use a consistent unit at all times. So 8 minutes is the average, therefore you need to write 0.5 minutes is the standard deviation, okay, not 30 seconds. Okay, if you write the location parameter is 8 and the scale parameter is 30, the units will not match, and of course you are going to answer it incorrectly. So 0.5 minutes is the standard deviation. So the question here is this: what is the probability that the next service will be complete in 400 seconds? So what is the probability that the next service will be complete in less than 400 seconds? It means will be complete in 400 seconds means in the first 400 seconds it must be complete. So how many minutes does 400 seconds make? By dividing it to 60, you can convert it to minutes. So we are interested in this probability actually. So let's just write it here. So we have the service time distribution for the teller service, which is normally distributed with location parameter equal to 8 and scale parameter equal to 0.5. So this is what we have. And here the question is asking, what is the probability of the next service is going to take less than or equal to 400 divided by 60, right? So how many minutes? 400 seconds. 400 divided by 60. So we are just going to write this as P norm 400 divided by 60, or simply 20 divided by 3, with location parameter 8 and scale parameter 0.5. Remember, now everything is converted into minutes, therefore the result is just going to be correct. And the probability that this service is going to be complete in less than 400 seconds is a very small probability, like 3.8%. Okay. How about the next question? It says, calculate the probability that the next service will take at least 9.5 minutes. So this time it says, what is the probability that the next service will be greater than 9.5 minutes, which is 1 minus the CDF at 9.5, right? So what I need to do is, I need to write 1 minus P norm 9.5 minutes. Again, the location parameter is 8 and the scale parameter is 0.5. And that probability is 0.0013, which is approximately 1.35%. Okay. And finally, what is the probability that the time to next service will take a time between 7 and 10 minutes? What is the probability that the time to next service will take a time between 7 and 10 minutes? Now, this time the question is asking us probability of the next service to be between 7 and 10 minutes. And of course, this is easy to calculate, the CDF at 10 minus CDF at 7. What you can do is P norm 10, 8, 0.5 minus again P norm 7, 8, 0.5. And that probability is 0.9772 approximately. All right, so there is another way of calculating this, which is integrating the probability density function, of course. So you need to write down the probability density function as a function with these parameters setting. And after integrating this PDF between 7 and 10, you are also going to get the same result. Now, the next question is the inverse CDF application question. So let's just say there is a certain building, and that building, the houses in this building using tap water, and the daily demand to tap water in that building is on the average 400 liters, and there is a variance is 225 liters square. So this means what? it is normally distributed. The daily demand to tap water is normally distributed with location parameter 400 and scale parameter. Of course, since this is equal to variance, remember the variance is equal to sigma square. The standard deviation or the sigma value will be 15. So you need to be very careful about this. The variance is 225, means the sigma value or the scale parameter or the standard deviation to be the square root of it, which is 15. So your parameters are, location parameter is 400 and the scale parameter is 15. So it says, find the amount that exceeds the daily water usage in 30% of the days. So every day, people are using different amounts of water, but that distribution is normal with location parameter 400 and scale parameter 15. So it says there's a certain water usage in liters which is exceeded by only 70% of the days, and in the remaining 30% of the days, that value exceeds the water usage. Okay, so it is basically asking this: find the x value for which the cumulative probability is equal to 0.30. So how we are going to do this? By writing the Q norm function, the inverse CDF function at 0.30 probability with location and the scale parameter here. Again, what amount of water usage is exceeded by 8% of the days? It says it means in only 8% of the days, the people are using more water than this X amount. In the remaining 92%, they are going to use a less amount. So accordingly, we are stating that the water usage on any day will exceed that certain usage amount with only 0.08 probability, which means 8% of the days. So this means the cumulative probability will be equal to 0.92 at x. Therefore, in order to find the x, we need to use the inverse CDF or the quantile function of the normal distribution at 0.92 probability with location parameter 400 and scale parameter 15. Now, it says in the last part, we need to write a comment which returns the amount of water usage which are exceeded by 20%, 40%, 60%, and 80% of the days. So again, we are looking for the x values for which the cumulative probability are respectively equal to 0.20, 0.40, 0.60, and 0.80. So this time we are going to use the Q norm function, but in the first argument, instead of writing a single probability, we are just writing 4 different probabilities, and this can be calculated by simple vector calculation here. And you see it says, according to the answer here, in 20% of the days, the daily water usage in this building is less than 387 liters approximately. In 40% of the days, the daily water usage is less than 396 liters. In 60% of the days, the daily water usage is less than 403 liters approximately. As you can see, this is more than 400. And one more thing that you can be observing here, these two values are symmetric around 400. These two values are symmetric around 400. Why? Because 400 is the average, and the probabilities 40% and 60% are also symmetric around 0.50. And finally, in 8% of the days, the daily water usage is less than 412. Only in 20% of the days, the daily water usage in this building is greater than 412 liters. Finally, in this last part, we are going to practice again the plot operation. It says we want to plot the probability density function of the normal distribution for standard normal distribution, the standard parameter setting, for normal random variable with location parameter 0 and standard deviation 2, and with location parameter 1 and scale parameter 1. And we are going to plot each probability density function with respectively black, red, and blue colors again. So by plotting the first plot diagram, the density function, and the second density function, we will see the effect of the standard deviation, how the standard deviation value changes the probability density function. And in the third plot, we will see the effect of the location parameter. We are going to draw these plot diagrams between -4 and 4. The lower bound and the upper bound of the plot diagram at horizontal axis will be -4 and 4. So we are just going to practice the same thing as we have done. I will just create a sequence between -4 and 4, and the length of these equidistant points between -4 and 4 will be 10,000. So there will be a vector of 10,000 points, as you can see, from -4 to 4. Let me see the first few values, for example, the first 10 values of this vector. It starts from -4 and it ends with 4. Now, in this plot diagram, I will write x versus the probability density function of normal random variable at values x with standard parameter setting. Even if I do not write anything, it will be assumed as standard parameter setting, and the plotted points will be connected with line. So the type of the plot is a line plot, and the width of this line will be 3 pixels, and the label, x label, will be x, and the horizontal y label, the horizontal axis label, will be fx. So if I do this plot, you will see the probability density function of a standard normal random variable has this bell shape, beautiful bell shape, which is exactly what you see here, right? So this bell shape from -4 to 4, the convergence is almost done. Remember, between 4 scale parameters from the mean, almost all possible values are introduced in the distribution. And the axes are labeled as x and the probability density function fx. Now I am just going to plot the second probability density function. But this time the parameters are going to be, location parameter will be 0 and scale parameter will be 2. So what I want to see is the effect of the scale parameter. So how does the distribution change if the scale parameter is increased? So how does the scale parameter change if it is increased to 2? And this time the color is going to be red. And let's see the results. So you see the bell shape this time has a greater variance. The peak point has been reduced. However, because the scale parameter increases, as the scale parameter increases, the distribution will be scaled over a wider area, a larger area. So this time, you will see that the convergence has not occurred yet. It is converging to 0, but there is still it is far from the tails of the previous probability density function. The convergence will occur maybe after -8 and +8. Okay, not -4, but +4. After -8 and +8, the convergence will occur. So the scale parameter increases the variation, of course, because the variance is equal to the square of the scale parameter. And according to this picture, the possible values that this second random variable, normal random variable, can take are distributed over a larger area. And let's see the effects of changing the location parameter. This time, we will say that we will have 1, 1 here. Okay, 1, 1 here. The location parameter will be 1, and the scale parameter will be again standard 1. And this time it will be blue. So what changes is exactly here. What changes is only the location of the distribution. So when the scale parameter stays the same as 1, remember, for standard normal random variable, the scale parameter was also 1. So the variation of the distribution is not affected. It still has the scale parameter, so the scaling does not change. Only the location of the distribution changes. Instead of distributing around 0, it is distributed around 1. In fact, I can show a vertical line at 1 here. Okay, sorry. And you see the center of the distribution is shifted to 1. Okay, it was previously at 0, and when you change the location parameter, it is shifted. Therefore, this changing the location parameter is called a shifting operation of the distribution. So the distribution is shifted 1 unit further, and changing the scale parameter is called a scaling operation. It increases or decreases the variance of the distribution. In fact, let's just draw an additional plot here with points function. So let's just say the location parameter will still be 0, but this time the scale parameter will be reduced to 0.5. Okay, so and this time we are going to color it with green. Okay, so you see the peak point even increase, but we cannot see this in this picture because our frame is generated by the first plot function. So the peak point increases to upside, and the convergence occurs very fast, even at -2. So the convergence previously occurring at -4 and +4 is occurring at -2 and +2 here. Because you have reduced the scale parameter, the variation of the possible values has been reduced. Okay. In fact, when you make the scale parameter equal to 0, you will not see anything because the variation will be 0, and there will only be a single value that this variable can take, which is the location parameter. All right, so that's the end of the second video, as you can see here. Thank you for listening.